Hi, and welcome to Codex. Our speaker today is Alhussein Fawzi, who is a staff research scientist at Google DeepMind. Dr. Fawzi is an expert in machine learning and its applications to mathematics and computer vision. Today, he will tell us about fast matrix multiplication. Take it away, Hussein.
Thank you very much, Joey and Dustin. It's great to be here. So yes, today I'd like to talk to you about our recent paper on discovering faster matrix multiplication algorithms with a technique of machine learning called reinforcement learning. This project started with a very simple question. The question was, can we discover new provably correct and efficient algorithms for impactful problems using machine learning? So there are three keywords here. The first one is provably correct, meaning that we're trying to find algorithms that are correct for all instances, for which we have a certificate of correctness for all instances. Efficient, meaning that we're trying to find algorithms that are efficient either like in terms of computational complexity or in terms of practical efficiency. And we want to study impactful problems, what we call root node problems, problems that play a big part of, that are central to many other computational problems. And we want to use machine learning in order to try to discover these algorithms. Or we want to understand essentially what machine learning can do in that direction. So if we're able to find automatically algorithms using machine learning, this can have a transformational impact because obviously, as you know, algorithms are used everywhere from your smartphone to supercomputers. So if we're able to have a technique to automate this procedure of algorithmic discovery, then this can be implemented in many different places. But there is a number of challenges with this. There is a number of challenges of using machine learning for this process of algorithmic discovery. One of them is obviously that the space of algorithms, the space of interesting algorithms is ill-defined, right? So it's very hard to define it as a clean search problem, for example. Because we're looking at algorithms and we're looking specifically at algorithms that are provably correct on all instances. Now, even if we're able to do that, even if we're able to express our search space, our algorithm space in which we're going to search, this is going to be very difficult to search in because as we'll see, the search space is just very large. So the standard techniques won't work out of the box. So we need really specialized techniques for navigating in such huge search spaces. So as I said, we'll be talking today about a matrix multiplication, which I'm sure you all agree that matrix multiplication is a root node problem in the sense that it's central to many other computational tasks, from neural network training to matrix factorizations to simulations and so on and so forth. So the outline of my talk is going to be as follows. First, I'd like to tell you a bit more about how we can formalize the problem of finding matrix multiplication algorithms as a machine learning problem. At the first sight, it might not be very obvious. How can you actually relate the problem of finding matrix multiplication algorithms as a machine learning problem? What's the relation between these two things? So we'll try to go step by step on how we can formalize that problem. The second part of my talk, I would like to tell you a bit more about the ingredients used to make machine learning work in this particular problem, but also beyond that in different math problems. And then I'll talk a bit about the results and concluding remarks. Okay, so first things first, I'm going to quickly go over that, but just to set the notations, matrix multiplication, I'm sure you're all aware of that. This is just the notation of matrix multiplication for 2x2 matrices. For a very long time, the standard algorithm of doing matrix multiplication was believed to be the optimal one, but in 1969, Strassen shocked the mathematical community by showing that you could do better than that, in the sense that he could find an algorithm to multiply 2x2 matrices using 7 scalar multiplications as opposed to 8. And the way he would do that is by combining entries of the first matrix you want to multiply, like by adding some of the entries together, and then adding some of the entries of the second matrix you want to multiply, So multiplying these in a rather bizarre way, and then distributing them also in a rather weird way, but then eventually what you get is the right result, right? So it's very easy to check that this algorithm is correct by just some algebraic manipulation, but it's quite hard to come up with such an algorithm. So Strassen's algorithm is multiplying two 2x2 matrices using 7 scalar multiplications, and that's very interesting not only for 2x2 matrices, but also beyond that, right? So because you can apply this algorithm recursively, if you have an n by n matrix, two n by n matrices that you want to multiply, you can apply this algorithm recursively, and you eventually get an algorithm of complexity n to the power log base 2 of 7, roughly n to the power 2.81. Okay, so now I'd like to tell you a bit more about how we can formalize this problem using the Tensor language, because that would be very relevant to us of how we can use machine learning to tackle this problem of finding new algorithms for matrix multiplication. So the basic idea here is that matrix multiplication is a bilinear operation. So just like linear operations, you can represent them as matrices. Bilinear operation, you can represent them as tensors. So there is what we call the matrix multiplication tensor. And this tensor is of dimension n squared by n squared by n squared if you want to multiply n by n matrices. So what does this tensor look like? Well, it's a tensor that is like all zeros, except you have a few ones. You have 8 ones for the 2x2 matrix multiplication tensor, and it corresponds essentially to where do you read your entries that you want to multiply and where do you write them. Okay, so for example, because matrix multiplication involves the operation of multiplying A21 times B12, and you write that in C22, you're going to put a 1 precisely in that entry of A21, B12, and then C22. Okay, and you're going to do that for all the 8 multiplications that are involved in the 2x2 matrix multiplication. So you end up with a 4x4x4 tensor that has all zeros except 8 entries in these locations, 8 ones in these locations. Yeah. Okay, so that's the operation of multiplying matrices. What about algorithms to multiply matrices? So today we'll be focusing on algorithms that can be obtained through a rank decomposition of this tensor that I just talked about. Okay, so tensor decomposition is just an extension of matrix rank decomposition, where you have sum of UQ VQ transpose. So here you have an extension of this outer product operation, the tensor product essentially. Okay, so what I mean by tensor rank decomposition is that you have this tensor and then you want to decompose it into a sum of rank 1 tensors obtained by UQ, tensor product VQ, tensor product WQ, where UQ, VQ, and WQ are all vectors. Okay, so my tensor T is of dimension n squared by n squared by n squares, and UQ, VQ, and WQ are all vectors of dimension n squared. Okay, so this is just a pictorial representation of what I just said. And the interesting bit here is that once you have a decomposition of this tensor, then you can automatically get an algorithm to multiply arbitrary matrices. Okay, arbitrary matrices A and B. And this is the algorithm essentially. And the important quantity here is the rank of this decomposition that automatically translates into the asymptotic complexity of the algorithm. Okay, so what we want to do essentially is to find low rank decompositions of this matrix multiplication tensor in order to find efficient algorithms to multiply matrices. And as I said, you can multiply matrices of arbitrary size through recursion, just like what we saw with Strassen's algorithm. Okay, so maybe to make the connection between what an algorithm like Strassen's algorithm, for example, and the tensor decomposition more concrete. So this is how you can translate from this language to that language. So you have here A11 plus A22 times B11 plus B22. So you have therefore the first factor, you have 1001, and for the second factor, you have also 1001. And the way you distribute this is described by the third dimension here. So because you distribute it both in C11 and C22, you distribute H1 in C11 and C22, you're going to also put a 1001 at the last dimension. Okay. Okay. So the problem really boils down to trying to find low-rank decompositions of the matrix multiplication tensor. Now, unfortunately, unlike matrices, for which there is a polynomial time algorithm to compute the rank of matrices, for tensors, that's not the case. So this is precisely where we're going to use machine learning for. We'll try to use machine learning to decompose this matrix multiplication tensor. So how are we going to cast this problem? Well, we're going to cast it as a single player game, okay? Our board is going to be this tensor that we want to decompose, right? So our starting board is going to be the matrix multiplication tensor. And then at each step, what the player can do is to select a rank 1 tensor of its choice, okay? And then you update the board by subtracting this rank 1 tensor that the player has chosen, and then you repeat for a fixed number of times. Okay, so we're going to repeat for a fixed number of times, and the objective of the player is to reach the tensor that is all equal to 0. The entries are all equal to 0. Okay, now you don't want to find just any path from this matrix multiplication tensor to the 0 tensor. You want to find the shortest path, right? Because you want to find a low rank decomposition of this tensor, right? It's not very hard to see that if you find the 0 tensor, then you get a rank decomposition of the matrix multiplication tensor, but we don't want just to find any decomposition, we want to find the shortest one. So because we want to find the shortest one, what I'll be giving as a penalty at each step of this game is a -1 reward, right? So that it's penalized each time it takes it chooses a rank 1 tensor. And then at the very end of the episode, if I don't reach the 0 tensor at the end, then I compute an upper bound on the rank of the residual tensor, and I'm going to give that as a final penalty if the player didn't reach this 0 tensor at the very end. Okay, so it's a very simple game where you have this 3D board, and then you want to find a low rank decomposition of that tensor. Okay, now, despite the simplicity of like the game, how we can describe the game, there are a lot of challenges associated with this game. In particular, there's a huge action space. So if you compare this, for example, to Go, where you have instead of 2D board and you have 19 by 19, around 360 actions at each step that you can take. Here you have an infinite number of actions actually that you can take, in the sense that there is an infinite number of rank 1 tensors. So that's a big difficulty. Now, even if we discretize the rank 1 tensors, and this is what we're going to do here, I'm going to discretize the rank 1 tensor, the entries of the factors in the rank 1 tensors we're going to consider, then still the number of actions that you're going to consider is very large to deal with the normal reinforcement learning techniques. You don't have training data in the sense that, for example, in Go, again, you have like expert demonstrations online, people who play the game really, really well. In this case, it's hard to get demonstrations in the sense that you don't have available data of tensors that have low rank decompositions. It's a slightly unusual setting for machine learning because you only have one tensor to decompose. So in many cases, in many machine learning settings, you usually care about the distribution of test data. That's what you care about. Here, you only care about this matrix multiplication tensor. If you decompose it, you're happy. If you don't, then you fail essentially. So the test data essentially is just made of one point, right? That matrix multiplication tensor. So it's a slightly unusual setting in the sense that there is not enough diversity, as we'll come to. There is a large number of symmetries involved in the problem of in tensors in general and the problem of tensor decomposition. So for example, if you take a tensor and then you permute slices, then you have the same rank. Obviously, like if you have a decomposition and you permute two factors together, then you have the same decomposition and so on. So yeah, just maybe to emphasize on the maybe comparison with Go, which I just alluded to. So in Go, as I said, in the last column here, you have a board size which is 19 by 19, and you have an action space which is 19 times 19 plus 1, 362. But when you in this game, when you discretize the entries of your factors, to, for example, -101 or -2, -1012, then you get an action space which is very large. For example, for the 2x2 case, it's 10 to the 8, and for the 5x5 case, it's 10 to the 52. Okay, so the procedure will be like the agent that will be training to play this game is going to be based on a tree search approach, where at each step we're going to do a lot of simulations, and then we're going to pick the rank 1 tensor that seems the most promising. We're going to update the board or the tensor, and then we're going to start again many simulations and so on and so forth. Now, the problem, as I said, is that the breadth of this tree is going to be huge because you have a huge number of actions. So we have to really pick a needle in a haystack at each time we make a decision. So in the beginning of our training procedure, what will happen is that the simulations are essentially going to be random, but then bit by bit, essentially, we're going to learn how to play better this game. Okay. So our agent that we're going to train to play this game, AlphaTensor, is based on AlphaZero. And AlphaZero is this general reinforcement learning algorithm that has been used that has been shown to play Go and chess and other games really well. And that is really the basis of our work here. So I'll spend some time to explain how AlphaZero works, and then the modifications on top of AlphaZero that we need to make this work on this tensor decomposition game I just described. So AlphaZero is composed of two components: actors and a learner. Okay, so you can think of actors as a lot of independent computers playing games in parallel. Okay, so what you're going to do is that at each step of the game, you're going to do like, let's say, 1,000 simulation. In the beginning, these simulations, as I said, are going to be roughly random, and you're going to pick the best action, and you're going to update your state until you finish the game. Okay. Now, as I said, you're going to do this in many, like you're going to play a lot of these games in parallel, and then you're going to send all these games that you just played, like they're not really good games because you just started. You're going to send all these games to the learner. Okay. Now, the learner, what it's going to try to do is that it's going to try to make sense of this data or imitate the games that have been sent to it by the actors. Okay. So precisely what we're going to do is that we're going to try to take the states, or like sample the states from the games that have been played by the actors, and then predict two things: the policy and the value. Right. So the policy is going to be a prediction of what was the next move that was taken by the actor. Okay, and the value is an estimate of the interestingness of the current state at which I am. Right. So in our case, for example, the value is going to be an estimate of the rank of my current state. Okay. So in our case, the state is going to be the tensor, and then the value is going to be an estimate of the rank of that tensor. Okay. And the policy is going to be what is the next action that I've taken. Okay. So as I said, the learner is doing a very simple thing. It just try to imitate the games that have been played by the actors, right? So try to just try to see, like, to train a neural network to predict what was the next action and what is the current, what is an estimate of the value or an estimate of the rank of my current tensor. Okay, so you train this network for some time, for a few gradient steps essentially, and then you send that network back to the actors. Now, the idea is that at the next stage, we want to improve a bit over the simulations, the Monte Carlo tree search simulations that we just did at the first step, right? So what we're going to do is that we're going to take the policy and value as a starting point, and then do a Monte Carlo tree search on top of that to try to improve over the policy and value that have been predicted by the network. Okay, so you can think of the Monte Carlo tree search as a policy improvement operator over the policy and value that have been proposed to you by the network. Okay, so at the next step, you're going to produce better games, right? So you're going to definitely, like, mimic the policy and value, but you're going to do some random exploration. And hopefully this random exploration leads to some better games than the ones that you've learned in the previous step. You're going to send the games again to the learner. The learner is going to try to imitate the improved policy and the improved values and so on. And then you're going to send the network and so on and so forth. So what you're going to get is a self-reinforcing procedure where you start from like actors that play really bad to actors that improve over time. And that's how you reach superhuman performance in Go and chess. So as I said, we're going to be relying on this approach, on this AlphaZero approach, but we're going to add a few ingredients to tackle some of the issues that, or some of the difficulties that I've mentioned before. In particular, as I said, we have a number of challenges. So I'll be describing 4 ingredients: synthetic demonstrations, diversifying the target, train a generalist agent, and the deep and tailored architecture. Okay, so synthetic data. So as I said before, if you want to have a good machine learning system, you need a lot of data. And in math problems, and this problem also in particular, abundant data is rarely available, right? So you need to rely instead on synthetic data. So this is tensor decomposition is one of those problems that where one direction is hard, but the other direction is really easy. So if you have a tensor, it's really hard to decompose it. But if you have the decomposition, right, it's really easy to get the associated tensor. You just need to sum the rank 1 tensors, right? So this is a very simple idea, but it's a basis for generating an infinite amount of training data, an infinite amount of pairs of tensor and factorization, right? So you can just start with random factorizations, random decompositions, and then you create the associated tensor by just summing these rank 1 tensors, right? So you have an infinite amount of tensor factorization pairs. Obviously, these need not be optimal in any way, but they provide a relatively good training data for the network to start, at least in the beginning of training. So you can incorporate any symmetries you have of your problem in this synthetic data. So say, for example, that you would like to find decompositions that have some symmetries, like, for example, if you have UVW, then you have also VWU and WUV, then you can also generate data with that symmetry so that you skew the network towards outputting decompositions that have the symmetry that you care about. So this is done in addition to the data coming from the actors. So before the slide before I showed the data is generated by the actors in a dynamic way. This is so what we consider is a hybrid data where half of the data comes from the actors and the other half comes from this random synthetic data. Now, obviously, the big issue with this approach of creating synthetic data is that this is very far from the actual target that we care about, right? Because eventually what we care about is the decomposition of the matrix multiplication tensor. What we're generating here is just random tensors. But we found that this is very useful, at least in the beginning of training, to tell the network about the rules of the tensor decomposition game, essentially. So that's it starts much faster than if you just use the data coming from the actors. Okay, so the second ingredient is to diversify the targets, so as I said, this is a slightly unusual setting where you have just one target that you care about. In some sense, the test data that you consider is just made of one point. And this is usually actually a problem, I think, in many mathematical problems where you have one theorem that you want to find its proof, or you have one tensor you want to decompose, and so on. So what we did here is to express this tensor, this matrix multiplication tensor, in many different bases. So in that way, you have an equivalent way of having. So you have an equivalent a representation of the tensor, but the machine learning system doesn't know that these are equivalent, or so it's treating all these tensors in so it's not treating them in an equivalent way, essentially. So whenever you have a decomposition, so it's very possible, I mean, that you have a better decomposition for one of these tensors after you change the basis than the original tensor, right? So whenever you have a decomposition, a good decomposition for any of the tensors in a changed basis, then you can apply the inverse change of basis and propagate the information about the fact that you found a good decomposition for all the remaining bases. So pictorially, the idea here is that you're getting closer to the training data. So again, remember that the training data is generated randomly. So if you apply a random change of basis to the matrix multiplication tensor, it's a bit of a hand-wavy argument, but like it might be that you're getting closer to the distribution of data that you trained your machine learning system on. So the third ingredient is really important, is to train a generalist agent rather than several experts. So one way to train your agent is, for example, to train it on a fixed size tensors. So to train it on tensors of size, for example, 4 by 4 by 4 to rediscover Strassen's algorithm. But that's much worse than if you train your agent on all sizes in parallel, like all sizes simultaneously. Okay, so in this, so for example, if you want to train it on large tensors, then what we found is that by training on small tensors and large tensors at the same time, what the agent will automatically do is that it would be really good at the small tensors, then the medium-sized tensor, and then the large tensors, and there would be transfer of knowledge between the different decompositions that it found from the different targets. So, for example,
sorry, can I interrupt?
Yes.
There's a question in the chat, if I can share it. It says, do you choose nearby tensors that share some of the symmetries of the matrix multiplication tensor?
You choose nearby tensors that share some of the symmetries. I'm not sure what do you mean by nearby tensors?
I'm not sure either.
So we train on all targets at the same time. So like you can think of all rectangular targets from 2 by 2 to 5 by 5, right? So any so tensors of size 4 by 4 by 4 till 25 by 25 by 25. We train all that simultaneously. Not sure. Yeah.
Thank you.
So the interesting bit here is that there is transfer between targets that we didn't really think there would be any transfer. So for example, if you decompose a tensor of size, I don't know, like 25, 25, 25, then it would really be helpful to actually have the other tensor trained with it, which is of size 16 by 9 by 16 or something like that. So the techniques that are being transferred from one target to the other, it's something that we don't understand really well, because one might argue that, okay, of course there is transfer between 4 by 4 by 4 and 16, 16, 16, because you can get the 16, 16, 16 one from the 4, 4, 4 one just by applying it 2 times, right? So for example, you can get a rank 49 decomposition just by applying Strassen twice, right? So obviously there is this, but what we saw is that there is much more than that. Actually, if you train all these targets at the same time, then there is this mysterious transfer that happens between the different targets. And also, this is something I described for different sizes, but it also happens across different fields. So if you train it on different fields at the same time, then it's better than training for each field independently. Okay, so one positive thing of this transfer, one positive aspect of this generalist agent is that you have better performance, but also it's more efficient, right? If you have to train one agent for each size, then that would be really difficult from a computational point of view. So the fourth ingredient I'd like to talk about is the importance of the architecture of the neural network that you train, how you design this neural network. So sometimes there is this misconception that just throwing a big neural network at it would solve everything. That's really not the case. And one needs to be very smart about, or at least try to put symmetries and so on in the neural network to try to solve the problem in a data efficient way. So one of the things that one of the components of neural networks that is really important is attention and transformers. And this is something that has been introduced in natural language processing, where so this is like really the key behind the major breakthroughs happening recently in natural language processing. And it's the idea essentially that you can learn how to attend between different entries of your data. So, for example, if you want to translate a sentence from English to French, one way to do it would just be to translate it word by word. But that would be a really bad translation, obviously. So instead, what you do is that you try to learn the relation between the different entries that you have in the input and the output, right? And this is at the basis of the architecture of transformers. So this is not something that is specific to natural language. You can do this for all domains, really, as long as you want to try to learn relationships between different entities you have. This is, for example, a big component in the protein folding breakthrough that happened a few years ago, and it was also something that we heavily use in the architecture for this project here. So how do we use these transformers for our architecture? Let's just maybe recap a bit what we want to learn here. So remember that we have a state that we take as input to our neural network, and then what we want to predict is two things, right? So the policy, which is going to be the rank 1 tensor, or the factors corresponding to the rank 1 tensor that I'm going to choose, and then the value, which is an estimate of the rank of the tensor that I have in the input here, right? So I want to predict these two things here. So the architecture we're going to use has a torso and then like three networks, essentially, a torso and then a policy network and a value network. So we found that the most important thing is to spend spend time on fine tuning or the torso, on getting the architecture of the torso right. So the architecture of the torso that we converge to eventually is as follows. So we have this tensor, as I said, that is the input of the neural network. And this tensor is quite big to work with. So you need to somehow like reduce the dimension of this tensor. So the first thing we did is to project this tensor into three grids of features. And loosely speaking, these three grids of features represent the like different views of your tensor, right? So this grid of feature A represents the view of the tensor along the first two modes. B represents the view of the tensor along the VW, and so on. So that's obviously like a more hand-wavy way of describing things, but this was really like this dimensionality reduction was really essential for doing attention, because attention is an expensive operation. Now, then once we have these three grids of feature, what we do is that we attend between different entries that belong to the same slice, right? So the idea here is that the entries that belong to the same slice are more related to each other than entries that belong to different slices. So it's normal that they talk to each other, that they communicate more than entries that belong to different slices. Now, one other benefit of this approach of attending only between entries that belong to the same slice is that your architecture will be invariant to slice reordering. And this is something that we know is the rank is invariant to the slice reordering. So it's something that takes into account the invariance of your problem. Now, obviously, like, you can try other architectures and they might work as well. So it's really, at this stage, it's really like an empirical, it's an empirical result really, other than like a theoretical one. But what we try to do is to try to impose some prior knowledge about the problem, and like if you constrain your network to have all the symmetries, then you're likely not going to be expressive enough, and therefore you're not going to perform well. But if you don't impose anything, then you're also not going to be data efficient. So there is really a middle ground between the two, and this is the best architecture we found. So the overall system looks something like that, in the sense that you have a tensor that you want to decompose. That is in the standard basis. You apply some random change of basis. You do your Monte Carlo tree search simulations. You get the games that I've been describing before, that obtained from the actors. You're going to send those to the learner, and then the learner is going to sample random states either from the games played by the actor or from the synthetic demonstrations, the random synthetic demonstrations. And then you're going to train your neural network to predict two things: the policy and the value. You're going to update the model. You're going to send it back to the actor, and so on and so forth. So this is the system, how it looks like. Now, in terms of results, as I said, we trained one agent to play all these different sizes simultaneously, or to try to find the decomposition of all these matrix multiplication tensors simultaneously. Now, obviously, for all of these targets, we have a tabulation of what is the best rank. What is an upper bound on the rank of all of these tensors. We decomposed these in different fields, in GF2, but also in R. And at the beginning of training, really, the agent doesn't know anything about matrix multiplication, so it's really bad. It finds essentially the normal algorithm, but then at some point it finds the Strassen's algorithm. And then you continue training, it finds like better and better algorithms. And then at some point it surpasses the known algorithms. Here, for example, for multiplying 3 by 4 times 4 by 5, it finds an algorithm for multiplying it with 47 multiplications. And then you continue training and you achieve essentially better performance, or better, like you find algorithms with better number of multiplications for all these targets here. So one of the results that we were quite surprised with is that we were able to find an algorithm to multiply 4 by 4 matrices that was better than Strassen's 2-level algorithm. So the rank 49 algorithm that consists in applying Strassen's algorithm twice. So the Strassen's algorithm twice has a rank of 49. So here we found rank 47. In fields of characteristic 2. So then you can take these algorithms and try to see, okay, like, can I interpret this? But then you get this algorithm. You can check that it's correct, but beyond that, I think it's quite hard to analyze. We've published all these algorithms online, but yeah, we found it to be quite difficult to analyze, obviously. Now, the agent that we trained is not only like outputting one algorithm for each of these sizes, but it's outputting like thousands of inequivalent decompositions for each target. By inequivalent here, I mean that you cannot find transformation from one to the other from a known one in a relatively simple way. So, for example, if you have a factorization of a tensor, let's say ui, vi, wi, then you permute the factors. So you have vi, wi, ui, then that's also an algorithm because the matrix multiplication tensor is cyclic. So that's a transformation that that defines this equivalence class. So what we did here is that we found thousands of inequivalent decompositions. So for each of these targets. As I said, we open source the data set of factorizations, and we hope that this can help better understand the space of matrix multiplication algorithms. And then beyond that mathematical aspect, you can also take this data set of algorithms that we found and then combine them, do some divide and conquer approach to try to decompose larger matrix multiplication tensors from the small ones. And in this case, the diversity really helps because it matters really which actual algorithm you're combining with which one. And we improved the ranks for many of the larger tensors. So the approach is really not specific to matrix multiplication in the sense that you can apply it really to any bilinear map. So we applied it, for example, for circulant matrix multiplication, and then you get the Fourier transform or the Fourier basis. And here we also applied it to a relatively niche bilinear operation, which is skew-symmetric matrix vector product. So what you do in this case is that you decompose it for n is equal to 3, 4, 5, 6, 7, and 10, and then you get these decompositions that look very similar, have a very peculiar structure, and then you can therefore extrapolate really and get an algorithm for multiplying skew-symmetric matrix vector products that is better than what was known before. So this approach of optimizing the rank is like, it can be used really to optimize any objective function as long as it's computable, because we're doing reinforcement learning here, and as long as the reward is computable, that's fine. So what we did to illustrate this idea is to use the runtime of the algorithm that you find on a specific hardware, which is a very difficult thing to optimize. It's a very stochastic objective function, obviously. So what we wanted to do is that to illustrate that you can optimize these difficult objective functions, such as the latency on a specific hardware. So it's exactly the same setting as before, but instead of giving a reward at the end, which is just 0 if you find, like a 0 reward if you find it at the end, or an upper bound on the rank of the residual, an upper bound on the rank of the residual tensor. Once you found the algorithm, you run it on this hardware, and then you send back that to as a learning signal for the algorithm for AlphaTensor to optimize for algorithms that are actually fast on a specific hardware. Okay, and the algorithms that you get are faster than the standard algorithms for very large matrix multiplication. So we tried it on two hardware, NVIDIA V100 GPU and TPU version 2. So the algorithms that you're getting are faster, as I said, with respect to the normal matrix multiplication, and slightly faster than Strassen's algorithm. Now, maybe one detail here is that we only apply one step of our algorithm, and then use the normal matrix multiplication algorithm for the smaller matrices. So you can think of this as a way to decompose a very large matrix multiplication into smaller matrix multiplication in a smarter way than what is done using the normal matrix multiplication operation. So the algorithms that you're getting for multiplying matrices are also quite specific to the hardware that you're considering. So for example, if you try to optimize for runtime on a GPU and then test it on TPU, it's not going to be as well as if you optimize it on TPU and test it on TPU too. And that's what the curve on the right is showing here, that you really need to optimize for the particular hardware to get the best performance. Okay, so that's it for my talk. This is my last slide here. So as I said, like one of the original goals of this project was to say, okay, like we build this amazing tools in terms of machine learning systems that are able to play complex games like chess and Go. So what we wanted to do here is to try to tackle the topic of algorithmic discovery and very hard combinatorial problems. I hope I convinced you that machine learning has an important role to play going forward on these hard combinatorial problems. Now, obviously, there is some limitations associated with this approach. In particular, for example, the fact that we discretize the search space, right? So it might be that we missed out on important algorithms. The fact that we discretize the entries of the factors to be, for example, from -2 to 2. In the case of finite fields, that's not a problem because we consider the whole thing, but for infinite fields, that's obviously a limitation. And then you obviously don't get any optimality promise, right? So you're getting an upper bound on the rank, but you're not getting any lower bounds. So I think what's quite exciting about this approach is that it's very general in the sense that you can tackle any bilinear operation. You can apply it to many other search problems. And in terms of spaces, it can work with the spaces that are relatively difficult to work with in standard optimization approaches like finite fields, and objective functions that can be quite wild, such as, for example, the arbitrary rewards such as runtime and memory and so on. So that's it for me. Thank you very much.
All right, thank you very much. Let's take a moment to click the reaction button at the bottom, and I'm going to choose to clap. I bet most of the audience chooses the same thing. Okay, and we'll stop the recording.